So first ones we just needed to graph so we could answer the questions. So if we graph that on Desmos, it looks something like this. So draw a little sketch of it. Mostly I'm drawing the sketch so that I can do the increasing and decreasing intervals later. So if you look at the graph and you find the domain and the range, we know the domain is the x values, the range is the y values. What do you notice about the x values? How far to the left does the graph go? How far to the right does the graph go? Infinity. Goes forever to the left, forever to the right. So negative infinity to positive infinity. Okay. What about the range? How far down, how far up? Infinity for that as well. So down forever, up forever. And that one, anytime you're not sure with those, one trick that you can do is you can zoom out a lot. Do you guys see how it goes down forever and up forever now? Makes it a little bit easier if you zoom out, and then you can see, oh, there is a squiggle in the middle, but that squiggle doesn't stop the fact that it is going down forever and up forever. Okay, so if we go back to that, now I'm going to label for my increasing and decreasing intervals, and which values do I use, the x or the y? I use the x values for my increasing and decreasing intervals, so I'm going to label the -5, and I'm going to label the -2.333. Okay, and then if I put my stick figure on the graph, how is he walking when he gets started? Down. He's going downhill, decreasing, and then he hits the minimum, and then what does he do? Goes uphill, and then he hits the maximum, and what does he do? Goes downhill. Okay. What is the x value for this arrow? Negative infinity, because it points to the left. What is the x value for this arrow? Positive infinity, because it points to the right. Okay, so his increasing interval is in between what two numbers? -5 and okay, -2.333. Okay. Yeah, so for increasing and decreasing, we always do x values. So it's in between those two. And then what do we put around the numbers? Parentheses. Parentheses will always work. Okay. For decreasing, for the first decreasing answer, what number should we write? Negative infinity. -5. What should we put around it? Parentheses. Okay. For the second answer, what should we put? Okay. Infinity. And what should we put around it? Parentheses. And then we can put a U in between, but it's okay if we don't. Okay. Max min. So we need our mountaintops and our valleys. Our mountaintop is up here, so we're just going to write the x and the y coordinate. So -2.333, 7.481. And then for our min, we're going to write our valley, which is -5, -2. How many x-intercepts did you guys get? 3. So 1, 2, 3. Should have had all of those points written down. So -5.655, 0, -4.211, 0, and -1.134, 0. And then I don't see it crossing the y-axis. Does that mean there's not a y-intercept? No. You have to go down. Okay, so sometimes you have to zoom out to see the y-intercept, and it happens to be down here at 0, -27. Okay, so there's our intercepts. For the end behavior, here it says as x goes to -infinity, so they're asking about the left arrow. What do we know about the left arrow? Wait, it goes up or down? Up. So the y value, that's talking about up or down. So if the y value is going up, then what should we say for the infinity? Positive, because the y value is going up. Okay. Now this one's talking about the right arrow because it says x. X in positive infinity means right arrow. So the right arrow is pointing which way? Down. It's a right arrow that's pointing down. So if we're talking about the y value of the arrow and it's pointing down, what should we write? -infinity because it's pointing down. Okay. All right. Next part. So with this one, we're gonna make sure we remember from last week. Yeah. After we finish the warm-up. Okay. So what do we do first thing? We type it in. Is the window probably going to be, are we going to be able to see everything on the screen that we want to see? Probably not. Okay, so I'm going to type it in. And then what am I going to do? And then I'm going to want to look at the table. Okay, so I've got it typed in. I'm going to click on the gear. I'm going to click on the table. And then what do I do with the table? Okay, so I'm going to click after the 2, and I want to watch the values as they go up and come down until they get negative. Okay, so this is a water balloon. So the water balloon has gone up in the air, come back down and hit the ground. Now what do I do? Go to the wrench. What number on the table is going to help me with the wrench? The biggest number. So what was the biggest number on the table? 27. Okay. So if 27 is the biggest number on the table, how does that help me now? Okay, so for my bigger y value, I'm going to pick something larger than 27. What number do you guys want to use? 40. Okay. Right here, I'll change it to 40. And then this is a good window. I can see what I want to see. Okay. First question says, what is the initial height? Are they asking for an x value or a y value? Y value. So if we remember about these questions, it goes up in the air, comes back down. T seconds, this is the t, so this is the x value. Is your t value, also known as your x value. And then this is the height over here, which is your h of t, which we know is our y value. Okay. So we know that our x coordinate is time and our y coordinate is height. Okay. All right, what is the initial height of the balloon? What does the word initial mean? Start. Yeah, where did you start? So what is the time when you get started? If you're running in track and they start the clock, what does the time start at? 0. So anytime you start something, you're always starting at 0. So if they're asking for the initial height of something, they're always asking you to start at a value of 0. So let's look at the table. At 0, you have 2.7. Okay. I'm gonna leave the sentences for the end. So I'm gonna go on to the next one. Next one says when. when does the balloon reach its maximum height? If the question says when, are they looking for an X value or a Y value? They want an X value. And if it says maximum height, what are we looking for on the graph? We're looking for the max. So we're looking for this point right there at the very top. Okay, let's find that. It's not from the table. I can see this point is not quite in the middle. So I'm going to click where the equation is, let the gray points pop up. And then I'm going to click on the gray point right there in the middle. So 2.245, comma, 27.394. Okay. The next question says, how high is the balloon after 2 seconds? If the question says how high, is that an X value or a Y value? Y, how high? How high is the balloon after 2 seconds? So the 2 they gave us is an X value of 2. So I'm going to look at the table and I'm going to see what my Y value is when I have an X value of 2. What's my Y value? 27.1. Okay. The next question says when is the balloon 20 meters high? If they're asking when, is that an X or a Y value question? That's an X value question. When is the balloon 20 meters high? So that means the 20 meters they gave us is a Y value. How do I plug in a Y value? I plug in Y equals. So I'm going to type in Y equals 20. That puts a line there. And then what do I do? I click on the 2 points where it crosses, right here and right here. Okay, and then I write those points down. Okay. All right, so now for each of these, you should have a sentence written. So this was Y, the Y value. This one was the X value. This one was the Y value. This one is the X values, and there's 2 of them. Okay, so for the first one, since it says, what is the initial height of the balloon? Your sentence should say something like the initial height of the balloon is 2.7 meters. When does the balloon reach its maximum height? You would say the balloon reaches its maximum height at 2.245 seconds. How high is the balloon after 2 seconds? The balloon is 27.1 meters high after 2 seconds. When is the balloon 20 meters high? You would say the balloon is 20 meters high at 1.017 seconds and 3.473 seconds. You'd be writing sentences for every single one of those. All right. Go ahead and put your name on the warm-ups, get them turned in. So last week we did problems on projectile motion. And the nice thing about projectile motion is that when you do those problems, they give you the equation and you can work from there. And then, like I showed you guys, the questions are all kind of similar. So today we're going to do another type of problem. These problems are all volume problems. They're volume of a box. And the nice thing about these, let's go ahead and put all the cell phones away, all the earbuds away. The nice thing about these is that these problems are very consistent. The kind of bummer about these is that they do not give you the equations. You have to write the equation. That's the first step. So the equation is written the same way every single time though. So that is kind of nice. So this is a really commonly worded question. You see them in Math 3. If you are planning on going to college and have to take the ACT or the SAT, you'll probably see them on those tests as well. It's just a really common question. So The problem says an open box with a rectangular base is to be made from a piece of cardstock that measures 8 centimeters by 12 centimeters by cutting out a square from each corner and turning up the sides. So before we do the Math 3 version of this question, I wanted to just show you guys maybe an easier version of this question. So we're going to go ahead and draw this 8 centimeters by 12 centimeters. And I wanted you guys to be able to picture this. So this is a piece of cardstock. It's just like paper. It's just like, you can tell it's like thicker than paper. So everybody's seen cardstock before. You guys know what I'm talking about with cardstock? Okay, so this is what we would start with. And then what they're saying, so that you guys can visualize it, is they took the cardstock and they cut out a square from each corner. Does that make sense? This is what they did. They cut out a square from each corner. And then once they cut the square out from each corner, they folded straight down this line right here. They folded up like this. And then from the other side, they did the same thing. They folded. And then they folded along here, and they folded along here. And if you do that along all 4 sides, you get a box that has no lid. Does that make sense? So as long as you cut out from all 4 corners, you can do that. You can make that box. This is that common question, okay? So what we're going to do is we're going to draw, okay? We're going to say, okay, you cut out a 1 centimeter by 1 centimeter square, and then you threw that part away. You got rid of it. You cut out a 1 centimeter by 1 centimeter square, and you threw that part away. Cut it out, threw it away. Cut it out, threw it away. Okay, so what they did first is they folded along this line and folded up that flap, and folded along this line and folded up this flap, okay? So the original width that we had for our box was a width of 8. But if you cut off a centimeter and folded the flap, and then cut off a centimeter and folded the flap, what's the new width? Because it's not 8 anymore. It wouldn't be 7, it'd be 6, right? Because you cut off 1 on one side, you cut off 1 on the other side. So you cut off 2, right? Okay, so I'm going to say 8 minus 1 from the left side minus 1 from the right side equals a new width of 6. Does that make sense? Okay. Now for the length, the original length was 12, but we cut off a centimeter and we folded the flap. We cut off a centimeter and we folded the flap. So if the original length was 12, and we folded off a flap on the top and bottom, what's the new length? 10, okay? So I'm gonna show in my picture, we folded these flaps. Okay, so we're gonna say, now the length was 12, we minus 1 from the top, we minus 1 from the bottom, we get 10 is the new length, okay? Now we have to figure out the height of our box, and this is the weirdest part, okay? All right, so you have to look up here. We have a square cut out from the corner. The square is 1 centimeter by 1 centimeter, right? Now, if I fold this up, look where the height of the box comes from. I fold it. So what's the height of the box? It's 1 centimeter, right? It comes from the square that I cut out of the corner. Everyone see that? So the height is 1 centimeter. Okay, has anyone ever heard that the volume of a box is length times width times height? Okay, so if I wanted to know the volume of this box, I would just multiply the length times the width times the height, right? Okay, so if I multiply these together, I get 6 times 10 times 1. And what is the volume of this box? 60. And then we would say we're finding a volume, so it would be centimeters times centimeters times centimeters, and so that would be centimeters cubed. And that would be the volume that that box could hold. All right, makes sense so far? We're comfortable? Okay, we're going to try this problem again, but we're going to think about cutting out a different size square. So we're going to start with the same sheet of cardstock. We're still going to have 8 centimeters for the width. We're still going to have 12 centimeters for the length. But this time we're going to say that we cut out a bigger square from the corners. We're going to say that we cut out a 2 centimeter square from the corners. Okay, so our width originally was 8. We originally had a width of 8, but we cut off 2 on the left side and we cut off 2 on the right side. So what's the new width? The new width would be 4. So we had 8, we cut off 2 on the left side, we cut off 2 on the right side. So the new width is 4, okay? So I'm going to say 8 minus 2 for the left, minus 2 for the right. The new width is 4. Okay, the original length was 12. We cut off 2 on the top. We cut off 2 on the bottom. What's the new length? 8. The new length would be 8. So we started with 12. We cut off 2 on the top. We cut off 2 on the bottom. And our new length is 8. How are your brains feeling? Does it make sense? So we're doing the same math we did last time. We just have a different number for the corner that we cut out. Okay. Now for the square corner that we have, it is a 2 by 2 square. When you fold up the flaps, what happens to make the height? What would the height be? It'd be 2. All right, so volume is length times width times height. And so we would say our volume is 4 times 8 times 2. And what would that give us? 4 times 8 times 2. 64. 64 centimeters cubed. Okay. Now these questions were just to kind of help us understand what's going on, but these are technically not Math 3 level questions, because in Math 3 we like to deal with variables. We like to have X's in the problem and have something we don't know, right? That's how Math 3 usually works. So with Math 3, we're going to start with the same thing. We're going to say, okay, we have that piece of cardstock. The cardstock is 8 by 12. We're taking our piece of cardstock, we're cutting out the corners. Doing the exact same thing we did before. But in Math 3, when we cut out our corners, they're probably not going to be whole numbers. So it's probably not going to be just 1 or just 2. It's probably going to be some sort of decimal. And we're going to plug in X. We're going to say, let's make a formula for it so we can see no matter what square we cut out, what would the volume be? Does that make sense? We're going to change it up. So I'm going to say the way that we always created the width is we took the original width of 8 and we subtracted the amount of the square from the left and we subtracted the amount of the square from the right. That's how we found our new width. Okay, so if I don't know how big the square is, I'm going to say 8 minus some unknown amount of centimeters from the left and the same unknown amount of centimeters from the right. So in the first example, we said minus 1 centimeter from the left, minus 1 centimeter from the right. In the second sample, we did minus 2 from the left, minus 2 from the right. And this overall would give us a width of 8 minus 2x. Now, remember I said this is consistent. So even though we're writing this equation ourselves, it is always going to be the same. Whatever the width is that they give you for the cardstock or the cardboard or the metal or whatever they happen to make the box out of, whatever the width is, you're always going to say the width minus 2x. It's going to be that every single time. It will never be minus 3x. It will never be minus 5x. It will always be the width minus 2x every single time. All right, now the length is going to be the length they gave you minus x for the left side, or sorry, top, minus x for the top, minus x for the bottom, equals 12 minus 2x. And it will always be that. Whatever the length is they gave you in the problem, minus 2x every single time. And then if you guys remember how we found the height, whatever the square was that they cut out, that was how the height was created. So if we don't know what the size of the square is, then that's going to be the variable we're still going to use. If it was a 2 by 2 square, then the height is 2. If it's a 3.7 by 3.7 square, then the height is 3.7. If it's a pi by pi square, then the height is pi, 3.14. If it's a 3.782, then it's a 3.782. Okay, so we're going to say that the height is just x. And that's what it's going to be every single time. Okay, so we're going to write this formula now. So they said V of x, the volume equals length times width times height. We already knew that, right? Volume is length times width times height. So we're going to say the volume is length times width times height. It doesn't matter which order you put these in. So I'm going to say 8 minus 2x, 12 minus 2x, and x. 8 minus 2x, 12 minus 2x, and x. I'm just going to put them in parentheses. I do not have to multiply this out. I'm just going to leave it like that. Now it's ready for Desmos. And from here, we're going to do it basically the same as what we did the other problems with, okay? So we have to keep in mind, what does the x mean, the thing we plug into the problem? What does the y mean, the thing that we got out of the problem, okay? So the x that we're plugging in, is the size of the cut out square. That's the x value, right? Because remember when we did the last application problems, we always said, oh, x was the time, y was the height. And whenever they gave us a problem, we had to figure out, are we solving for x or are we solving for y? We're going to do the same thing for this. So the x is the size of the cutout square. The y value is what happens when your x's are all plugged in. So all my x's are plugged in, I get my y value, which is v. It is length times width times height equals v. And so what is my y value going to give me? Length times width times height. Not a specific number, but what does it give me every time? Volume. It's going to give me the volume of the box. If you cut out this size square, your volume of the box is whatever it happens to equal. So my y is going to be the volume of the box. X is the size of the cutout square. Y is the volume of the box. So when we look at the question and we see what it's asking, that's how we're going to know if it's an X value or a Y value. Okay, so let's get this plugged into Desmos. Gonna delete all these equations from the warm-up. I'm gonna hit the home button so I go back to normal. Now I can type the equation in. So I'm gonna have 8 minus 2x, 12 minus 2x and x. It looks exactly the same as what's on my paper. So everybody should be typing that into Desmos on your own Chromebook. You can put y in the front if you want, y equals. I don't know if Desmos likes v of x. We can try it. Yep, v of x is fine. And then we want to see how to change the window so that we can see exactly what it is that we want to see. So once I've got this typed in, I'm going to click on the gear and then click on the table. And what happens is, as you cut out bigger squares, the volume gets bigger at first. And then eventually you're going to cut out a square that's so big that you can't possibly make a box from that. So the same thing is going to happen as what we had happen with our last problems with the projectile motion, where we had the water balloon would go up in the air and then it would come down. Same thing is going to happen with this. We're going to see the volume of the box get bigger. And then once the square that you're cutting out gets too big, we're going to see the volume of the box go back down again. So I'm going to click enter. I'm going to watch the volume of the box get bigger and then smaller. Now, is it possible to have a negative volume for a box? Nope. Once we hit that negative volume for a box, we know we've got enough information. So you're looking for the table to do the exact same thing as what we saw last time. We just look for it to get to the biggest number, then we look for it to hit 0, and then we know we have found enough values. Okay, so what's the biggest number we see on the table? 64. So I'm going to go over to the wrench. I need to change this to something bigger than 64. 75. Okay. Now that feels a little close to me, so I'm going to zoom out a little bit. There we go. Okay, so there's our graph. And now I'm going to start going to my questions. All right. It says, first question, and actually the first 3 questions are all phrased the same. What is the volume? What is the volume? What is the volume? So if it says, what is the volume? Am I looking for an x value? Am I looking for an x value or a y value? I'm looking for a y value for all of those, because it says, what is the volume? Y value, y value, y value for all 3 of those. So that means for all 3 of those, they gave me an x value to plug in. So x value to plug in is 1.25. X value to plug in is 2.3. X value to plug in is 4.5. For all 3 of those, they gave me an x value to plug in because they said, what is the volume? Okay, so I'm going to go back to Desmos. And I'm going to click on the table, and it doesn't matter where you click. You guys can see that none of these x values are decimals. So I'm just going to click on one of them. It doesn't matter where. I'm going to choose a negative one because the negative ones aren't helpful to me. I'm going to delete the number, and I'm going to type the number I want, 1.25. So the answer for number 4 is the coordinate 1.25, comma 65.3125. And I'm going to leave that there. I'm going to write my sentences when I'm all done with all the answers. So I just typed this into the table, 1.25. And then I got 65.3125. I'll go ahead and press enter. It'll give me another space. Now I can type 2.3. That's my answer for 5. 2.3, comma, 57.868. Press enter. That'll give me space to write the next one. This one is 4.5. 4.5 gives me negative 13.5. Okay, so now I'm going to go back to my notes. So for all 3 of these, I was able to type the values into the table. And for all 3 of these, the y coordinate is the answer. Okay. So what is the volume if a 1.25 centimeter square is cut out, and I'm going to say if a 1.25 centimeter square is cut out, the volume is 65.3125 centimeters cubed. If a 2.3 centimeter square is cut out, the volume is 57.868 centimeters cubed. This one gave us a negative volume. Is that possible? No. So if my piece of paper originally was 8 by 12, can I cut from the left side 4.5 centimeters and cut from the right side 4.5 centimeters? That doesn't make sense, right? Because what is 4.5 from the left side and 4.5 from the right side? 9. And how wide is my paper? 8. So if I have to cut 9 inches just from the square corners alone, I don't even have enough paper for that. Okay, so that's what it means when you start to get to a negative volume. You have a situation that you can handle mathematically with the equation, but with the context of the problem, it just doesn't make sense. Okay, so we're going to say there is not enough paper or cardstock. There's not enough cardstock to cut out 4.5 centimeter squares. No. No negative volume. There's not enough cardstock. Okay, go ahead and flip the page. All right, this question says, there's a few questions, so we're gonna have to answer a few of them. It says, for what size square? For what size square? Is that an X value or a Y value? That's an X value. Okay, for what size square is the volume the largest? What are we gonna look for? We're gonna look for the Y, because it says the largest volume, but where on the graph are we gonna look? Wait until we're done with the notes. Say that again. The biggest number, what's that called on the graph? The max. We're gonna look for the max. So let's go to Desmos. And is there a max in the picture? Yeah, right now I can't see it. These are the table numbers. I can't see the max here. So I'm gonna go and click next to the equation, wait for the gray dot to show up, and then I can click on the gray dot. There's the max right there. So I'll go ahead and write down that point, 1.569, comma, 67.604. The X value is the answer. So for what size square is the volume the largest? The volume is the largest for a 1.569 centimeter square. Okay. Now we finished the first question, but we got 2 more questions to do in that same problem. So the next question says, what are the dimensions of the box with the largest volume? So what does the word dimensions mean? Has anyone heard of the word dimensions? Outside? Or if they said dimensions of a room, dimensions of a school, measurements. So if they said, what are the measurements of the box? What could they be talking about? Length, width, and height. What are the dimensions of the box? They're talking about the length, the width, and the height. So we had formulas for all of these. The width was 8 minus 2x. The length was 12 minus 2x. The height was just x. So we have an x value now, 1.569. And if we want to find the dimensions of the box, what should we do? Yeah, plug it in. Okay. All right. So I'm going to type these into Desmos. 1.569 is the x value. So for my dimensions, I'm going to say 8 minus 2 times 1.569. 12 minus 2 times 1.569. And then the height is just 1.569. So we have width, length, height. Those are the dimensions. Okay. Now, the way people typically write dimensions is they use the word by or they put an X there. So they would say the dimensions of the largest box are, and then they would write down, let me see what my decimals are. They would say 4.862, 4.862 centimeters by 8.862 centimeters by 1.569 centimeters. I use the word by instead of the little x's. So they could write it like this way, are 4.862 centimeters by 8.862 centimeters by 1.569, or instead of the word by, they put a little x in there. Okay, we have a third question. The third question says, what is the largest volume? Is that an x coordinate question or a y coordinate question? What is the largest volume? That's a y coordinate question. The largest volume is, the largest volume is 67.604 centimeters cubed. Okay. Next question says, what size square? X value or Y value? What size square? That's an X value question. Okay. What size square could be cut out that would give a volume of 50 centimeters cubed? So when they say the volume is 50 centimeters cubed, what coordinate are they giving us? They're giving us that the Y is 50. So what do we do with that? We type in Y equals 50. Okay, I'm going to delete these. I type in Y equals 50. Okay. I see 3 answers. One of my answers has cutting out a 6.693 centimeter square. Can I cut out a square that is 6 centimeters? No. So what happens is you can see that you have your volume and your volume dips down and is negative. See that? And then it dips back up again. This whole part of the graph over here doesn't make sense. So we can ignore this part of the graph. This part of the graph is good. We like it. This part of the graph doesn't make sense. And that is true for all of these problems. We only use the left side of the graph. We don't use the right side of the graph. Okay. If you forget that, you just have to think about, do your answers make sense? Because that right side of the graph, the answers will never make sense. Okay, so we've got 2 answers. I'm going to write both of them down. I got 0.723 comma 50. And I've got 2.584 comma 50. And for this one, I usually don't make students write a sentence because it would be a really long sentence. But the question says, for the next part, write the dimensions for all options. So what does dimensions mean again? Measurements, length, width, height. So I'm going to write these down again. We got 8 minus 2x, 12 minus 2x, and then just x. And we're going to have to take the x value that we just got, and we're going to have to plug it in. And we're going to have to plug it in for each one. So for the first one, we're going to have 8 minus 2 times 0.723, 12 minus 2 times 0.723, and then 0.723. So the width is 6.554. The length is 10.554. And the height is 0.723. So this is the answer to the first question. These are the answer to the second question. .584 centimeters. There's the answer to the first question. There's the answer to the second question. We're almost done. All right, the next one says, what size square? It's an X value question. What size square? It says, what size square could be cut out that would give a volume of 46 centimeters cubed and would minimize waste? So they gave us 46 centimeters cubed, so there's our Y value. And so we're going to start with this, and then I'll help you guys figure out the minimize waste part. So we're going to go back to Desmos. We're going to plug in that 46 and get those first answers. So plug in right here. We're going to go to 46. We know that the third answer is going to be too big. That square we cut out is just not going to work for the problem ever. So we're always going to ignore that one. Let's look at the first two. So I'm going to write both of these down. So I've got 0.638, comma, 46, and I've got 2.71, comma, 46. So I've got both of those written down. So both of those would achieve the goal, and the goal is to have a box that's 46 inches cubed. That's the goal. Now, the second goal is to minimize waste. It's to minimize how much you throw away, okay? So when you make a box, you cut out the corners, and what do you guys think they probably do with these little corners they cut out? They probably throw them away, right? So we have two options. We can cut out a square from the corner that is less than 1 centimeter. So it could be less than 1 centimeter by less than 1 centimeter. We take that square, we cut it out, we throw it away. Or they can cut out a square that is almost 3 centimeters. So we've got one that's less than 1 centimeter, one that is almost 3 centimeters. So we've got less than 1 centimeter square, less than 1 centimeter square, less than 1 centimeter square, less than 1 centimeter square. We throw them all away. Or we've got almost 3, almost 3, almost 3, almost 3. We throw them all away. Which one produces less waste? Less than 1, less than 1, less than 1, less than 1. How much area is that if it's less than 1, less than 1, less than 1, less than 1? 1. It's about 4, right? And then if we have almost 3, almost 3, almost 3, almost 3, how much is that? It's about 12. So which one is less? Yeah, it's always going to be the smaller one. Whichever square is smaller, that's going to be the one that produces less waste. So if you want to make a box of a specific volume, whichever one is smaller, that's the one you go with. The one that's bigger produces more waste. You always go with the smaller one. So a 0.638 centimeter square would make a 46 centimeter cubed box and minimize waste. All right, that is it for the notes. I think we'll stop for today because tomorrow we'll do our warm up and then we can practice doing those problems. So we are good for today.